Okay, let's go down memory lane for a second with regard to integral calculus, just like we did with differential calculus in the previous Pencast. If you remember, we started talking about reminding ourselves that velocity at any time t is the derivative of position. And then we said, okay, what if we wanted to know the position at any time t given the velocity? We would have to anti-differentiate. We would have to go backwards. And we used this indefinite integral symbol for an antiderivative, and we said that it's not obvious why you would choose that symbol. It means most general antiderivative, but why would you use that symbol? And we said you'd see that later at the end. We practiced taking antiderivatives, right? We took our differentiation shortcuts that we learned in the first semester and went backwards. I do need to back up and say something about, well, the first part of the semester. Originally, a definition of derivative involves a limit, right? Calculus is a method of calculation based on a concept of limit. So we originally evaluated limits by tables and graphs, and then we started doing them algebraically. Okay? We first evaluated our derivatives, since they involved limits, by tables and graphs, and then we went to algebraically. We computed derivatives by the definition of derivative, both of those definitions. But that's not efficient, right? So we spent a lot of time learning derivative shortcuts. So when we anti-differentiate, we go backwards on those shortcuts. All right. So then we turned our topic. So this was indefinite integrals. And then we turned our attention to a seemingly totally different topic. We looked at the problem of area under a curve. Okay? From x equal a to x equal b. And we first estimated this area by using a Riemann sum, right? A Riemann sum is f of x sub I star delta x. Okay? We partitioned this x-axis between a and b into n equal subintervals. We formed a rectangle over each of those subintervals. We picked an x sub I star in each, in the ith subinterval, and we picked an x sub star in each subinterval. We either picked a left-hand endpoint or a right-hand endpoint or a midpoint, and we let the height of the rectangle be f of x sub I star. And so we approximated the area under this curve with just by adding the areas of n rectangles. Okay? And if you just use 3 or 4 rectangles, you're not going to get a good approximation of the area. Although if you use midpoints rather than left or right-hand endpoints, you get a better approximation. But to get really good approximations, you have to use lots of rectangles. Then what did we do? We didn't use 4 or 6 rectangles. We used n rectangles. And we took the limit as n approaches infinity of our sum as I goes from 1 to n of f of x sub I star delta x. So we found what? The exact area under the curve by computing this limit. But this notation gets cumbersome, so we rewrote that like this. And we call this a definite integral. Okay? Now, these two problems of anti-differentiation and definite integration seem totally unrelated. but there's a connection. And that's the fundamental theorem of calculus, which says to evaluate a definite integral, to evaluate this limit of the sum, there's a shortcut. And what you can do is you can find an antiderivative of this function and plug in the endpoints. So for example, the definite integral from a to b of x squared is just x cubed over 3 evaluated from a to b, which would be b cubed over 3 minus a cubed over 3. So the reason we used this symbol for most general antiderivative and called this thing an indefinite integral was that we just stole this notation from the definite integral symbol. And while an indefinite integral and a definite integral mean very different things, an indefinite integral is an antiderivative. It's a function. A definite integral is area under a curve, or net area under a curve. It's a number. It's a limit of a sum. The two are connected by this fundamental theorem of calculus. So that's why we stole the integral symbol notation from the definite integral for the indefinite integral. It's because we knew that the shortcut for computing definite integrals would involve an indefinite integral. So thinking back to calculus is a method of calculation based on the concept of the limit. We two big branches of calculus, differential and integral. In differential calculus, the big problem was find the slope of a tangent line, find the instantaneous rate of change of a function with respect to its input. The big problem of integral calculus is find the area under a curve. When we first found slopes of tangent lines, when we first found areas under curves, we did this using the definition of, in the first case, derivative, and in the second case, of definite integral, and actually found this definite integral by finding the limit of a sum, right? We did that on one homework problem. And we did lots of homework problems at the beginning of the semester evaluating derivatives using the definition, actually taking the limit. But then for efficiency in derivatives, we learned bunches of shortcuts. And for efficiency in definite integrals, we learned the shortcut, which is the fundamental theorem of calculus.